did it just so that we can watch the video. Nope.
Try the 480p.
Nope. This one works.
Yay for flash coding problem.
Yeah, looks that way.
What?
version.
Correct?
That's right. First is really all about getting
So I'll just
kids.
use our imagination.
Yeah, it will crash if I click something else. But you guys can remember that, right? I mean, since it's not related to the class, you can remember the link, where to find it. All right, let's go ahead and take a look at the exam questions. As much as we don't want to do it, it is something that is actually important to do. Oh, actually, it did show this time.
Oh.
Okay. First, there you go. Okay, which one should I look
Get in the
This
game.
one here?
That one right there.
Get in the game.
It was cool.
Aww.
Click away on the tab and come back.
Not close it. Click on. And that's why I don't use Debian anymore.
I thought if I bang my head against the wall enough times, I can get through the wall.
Robots are the cutest trick.
Apparently, that's a really difficult thing to do. When you go to a 4-year university and you take quantum physics, your professor will probably tell you that, well, if you try enough times, it is possible because of the tunneling effect.
They tell you that here.
Huh?
They tell you that here in physics.
Really?
Yeah. Actually, one of the experiments was to try that, and you could get extra credit if you wanted.
Well, the probability is always there. You can also get, parts of your body through the wall and the other part is still on the other side. That would not be good. All right, so we are back to our usual stuff, kind of boring, and this time it's kind of, it's kind of long. Okay. So what we want to do today, the first thing we want to do is to take a look at the exam questions. And basically, I want to talk about, what the solution is and what I'm looking for when I grade it. And there are several versions of the first question, several versions of the second version, and so on and so forth. They're all pretty much equivalent. They're not exactly the same, but they are equivalent. So let me go ahead and open up one of these. And this time I'll try this program called Zernal, which is an interesting program. On the surface, it looks like a PDF reader, just like the other ones that you get. But this is actually a notebook. It's basically an electronic notebook application. So what I can do is I can actually circle stuff. I can add my annotations and whatnot. You can do it to any PDF, which is really a great tool, especially if you have a tablet PC. It's a great tool to use it.
Can you increase the font size a little bit?
I believe so. You just have to find the magnification tool.
Did you zoom?
Zoom in. Okay. That's a little bit big.
Control A and then select Sans 12 up in the corner.
That's okay. We don't really need to see all that much, because the instruction in question is this instruction here. Okay, so we are basically trying to implement one single instruction using a whole bunch of restrictions. This is the instruction that we are trying to implement, and we are trying to use all these restrictions. We have to play by the restrictions and still be able to accomplish what this instruction does. This is a move instruction. In other words, it is moving something from the left-hand side to the right-hand side. The left-hand side, or the first operand, is the source operand, and the second operand, or the right-hand side, is the destination, which is kind of backwards when you think about assignment statements. If you think about assignment statements, the right-hand side is the source, and the left-hand side is the destination. And the key is not, the right-hand side is easy. The destination is just an 8-bit register, so we don't have to worry about that one too much. The source is complicated, but it's not really that complicated because it is really just the most general form of a memory operand. And the most general memory operand is described here. It has a D, which stands for displacement, a B that stands for a base register, I stands for index register, and an S that stands for scale. And that's exactly how the syntax looks like, and you can see the resemblance between the first operand and the most general form of a memory operand. Are we doing okay so far at this point? Okay. And then here, I also spell out, what is the effective address. So the effective address, if you look at this part here, is the summation of DB and then I times S. Nobody asked me in this class, whether we should perform the addition first or whether we should perform the multiplication first. So I'm guessing that all of you know that you have to perform the multiplication before the addition. And is that assumption correct?
They didn't cut that math class yet.
Well, trust me, in cisp310, which you took from me as well, there were quite a few people, who did not know, whether they should what is the proper order when you see multiplication and addition without parentheses.
Do people like that pass your class?
I do not know.
In the most general.
You might have some classmates right here, who might have made that mistake once in cisp310.
Well, making the mistake once is one thing.
Yeah. I don't think those students will make the same mistake twice, because they learn, okay, multiplication first. That's pretty easy.
But then they see a division sign and go, oh no, I don't know this one.
Okay, so we have this, we have all the pieces available, and the restrictions is, okay, let me use another color because now we can make it more colorful. The restriction is you can only use operands that belong to the immediate type, register type, and indirect type, which is basically the only memory operand that you can use is the indirect. That's the only one that you can use. I also spell out here that you can use ECX, CX, CH, and CL as temporary registers. In other words, if you worry about destroying EBX or EDX, because the instruction is not supposed to destroy those registers or change the value of those registers, go ahead and use ECX or any variant form of the ECX register as a temporary register. Okay? Are there any questions at this point about the nature of the question, what it is asking? Okay. So basically, what we have to do is to perform this calculation and then put it into a register. To put the effective address into a register, and then we can use the indirect operand to accomplish the source operand in the original instruction. Are we kind of doing okay so far? Okay. Now you can only use the instructions that you can use. You can only use add and move, as the instructions. Now at this point or at the point of this examination, even the compare instruction is out of the scope of the question, and that's why I had to change the other question. Instead of using compare, I have to change it to using subtraction because subtraction is basically the same thing. So in this case, we only have 3 instructions to talk about. This one restricted to only 2 of the 3 instructions that we have talked about. Okay. The first thing, there's really no specific order to do this. If you want to be smart, you can use adding a register to itself to double the value of the register. If you want to do it like super duper smart, but it does not ask you for the most optimal solution. So if you want to do it the longer way, but you know for sure that works, you just have to add something 4 times to multiply it by 4. Is that okay so far? So what we're going to do is we'll take a look at the proposed solution, or the solution that I think is going to work. The first thing I want to do is to initialize the register ECX because something might be in the register already, and that's why you have to use the move instruction. So we'll move an immediate 0 into ECX because I already told you that ECX is a register that you can use, that you can change, and it's permitted by the question itself. The rest is really just doing this computation here, d plus b plus I times s. In this case, we already know the scale is 4, which means we have to multiply the value of edx by 4. So I'll do it the long way. I would basically say we'll add edx to ecx 4 times. So definitely not the quickest way to do it, but it will work for sure. Okay. Is that okay so far? Okay. What else do we have to do? What else are we going to add to ECX, which is the sum of all the terms? We have to add the base register, and we also have to add the displacement. The base register in this case is EBX. So we say add L EBX to ECX, and then the displacement, which is in this case is L1. We have to say add L. This time we have to say $L1. It is not just L1 itself. It is $L1 to ECX. And then we have one more instruction down here to move B indirect ECX to the destination, which is AL. And that's it. That's the solution. That's basically what it is all about. Okay. Are there any questions at this point? Now, in this case, interestingly, I did not intend it as such, but in the end, it actually is, one of the things that helps you in the end. Is I think, if I did not place the restrictions that you have to use one of these operands, some people might have accidentally used a direct operand here, and just say L1, okay? But the restriction in this case is going to help you because it says, you cannot use a direct operand because it's the wrong operand to use anyway. Okay, so people will be forced to use $L1, which turns out to be the right solution. That turns out to be the right answer. Okay, are there any questions about this? I know the last instruction is kind of, I did not prepare enough space for that.
We were able to see it earlier. We were able to see the last instruction earlier.
You want to see the last instruction? How about I put it next to this one here? Move B %ECX, because the effective address is already calculated in ECX, so you have to use the indirect operand with ECX and then move whatever ECX is pointing to AL, which is an 8-bit register. The rest of the program is really just to set it up so that you in case we go to the lab, you have something to test it with, but it's really pointless. When you do it on paper, it really is just translating one single instruction into the multiple instructions that can do exactly the same thing. Okay. Any yes?
Why do we need to do the L1 5 times instead of just 4?
This one does not place a restriction of how many times you can use a particular instruction.
My question is why we need to use 5
Because you
times?
have to multiply EDX by 4 first.
Yeah.
So by adding EDX 4 times into ECX, ECX becomes 4 times EDX.
But we have
It's 5 times here.
But that's an EBX here.
EBX.
That's an EBX. And then the last one is $L1, which is the displacement that is outside of the parentheses. So basically, what I'm looking for is something that looks like this. People may be adding the wrong number of times. So the wrong multiplier is applied to EDX. But as long as I can see that there's an attempt to do the multiplication, there will be some partial credit. Adding EBX to the sum, that one has to be there to get the partial credit because it is, the base register. And then this one here, I might give people partial credit if they forget that this has to be an immediate operand and forget to use the $sign in front of the immediate operand. Yes, sir.
I am.
Yes, I am.
I'm a little confused. I'm here on behalf of my son who's hoping to add a class of viewers from the waiting list, but there's a BizTech class in the room that's listed.
That class is going to meet next Monday, so we are not meeting today.
Okay, well, he was on the wait list for the Tuesday, Thursday section. So it
Tuesday,
should,
Thursday section.
yeah, one section number with something 66, and the one over there is listed as 68.
I'm not teaching any classes on Tuesday, Thursdays that is starting. Are you talking about the second 8-week class?
Yeah, second 8-week class.
The only second 8-week class I'm teaching is VBA, which is the Monday class, Monday evening class.
Well, it's funny because it said in the catalog that there were 2 sections, and he signed up for the Tuesday, Thursday section and is waitlisted for it.
And I'm the professor for that class?
Yes.
Do you remember the name of the course?
Yeah, VBA, actually, he texted me with all the information. I'm sorry to interrupt you, but I've been wandering around for a half
Is
an
it,
hour trying
is
to
it
figure
VBA with a
Yes,
visual
it is.
basis for application?
Yes.
It is a Monday only class. It's a Monday evening class.
See, that would be section 15168, that's listed over there. But
Okay,
he
but
signed up for
hold on.
15166.
But there's no
Which
meeting
is
time
Tuesday,
on
Thursday.
Tuesday. There's no Tuesday, Thursday meeting time.
I wonder why the computer would say there is then.
I can
Because
double
he's
check.
waitlisted number 14 for a course meeting right now.
Okay, just
Next
hold on
month.
a second. I hate to be.
I can call you during your office hour tomorrow or something if that.
No, it's fast enough. I can just check it right now. Just hold on a second. So spring 2011, main campus. That's a CISP.
Besides that, I think I did.
There's no Tuesday, Thursday meeting time. It's a Monday only class.
That's so weird.
It's right here. It's a Monday meeting
Yeah,
only time.
I see what you're saying, and in the computer there was a Tuesday, Thursday section listed,
No.
and he waitlisted for it, and he's on the wait list number 14.
Okay, he might be on the wait list, but we are not meeting until next Monday.
Well, I'll have him look at it and again in more depth.
Okay.
Would you have office number where he could call?
It's 484-8250.
8250. Thank
Yep.
you.
Mm-hmm.
Thank you. Sorry for interrupting.
All right.
That's what I was thinking at first.
That's interesting. Okay, back to our stuff. Okay. So are there any questions about this question here? What are we looking for? And the last instructions obviously is very important too. You get full credit if you spell out the entire thing and then it is at the right position, which means it has to be the last one. If anyone gives me this instruction but did not specify the byte, that would get partial credit, because I really hate to take all the points off just because the length of the operation is incorrect. Now, having said that, the length here or the width of the operation is actually very important, but in this case it is not as important because the second operand is already specifying this is a byte-wide operation. If you had an assembler, it will complain and say the instruction, if you use move L here and use the %AL here, the assembler would have complained and say, oh, this is not consistent, I cannot do this. Okay, so it's not really a bad problem, it's just not entirely correct in that case. Okay. Yep.
So a way to look at that problem is to move the effective address of that I times S plus B plus D into AL, pretty much.
You are moving the byte at that address into AL, and that's why the last instruction has a indirect operand. We are treating the value of ECX as an address, and then we go to that location and grab that byte and then copy that byte to AL. Okay. Yep.
I think I did something where I did move long and I did the indirect ECX into regular ECX, and then I moved byte percented CL into AL. That kind of maybe splits that up into 2 commands, or does that not work?
I have to take a look. I cannot, during the class, I cannot look at individual answers,
Right.
so I can't really quite, tell
I
you
was
what.
wondering if that would accomplish the same.
Well, now that you know what the solution is, you can actually test it, because I will save it and then we can upload it, and then you can test, the your solution against the what it is supposed to accomplish. Okay. So that is that. So I'll save this file first, and it will save it as a Zerno file. I'm not sure what Oh, Zerno has a Windows port, so you can actually download and install Zerno on your home computer. Then you'll be able to open up these files. The objection to have to install another open source program for this class?
You might have to read the source code. I don't know.
I don't know. It sounds pretty expensive to me. Okay, so that's the first one. Let's go ahead and take a look at the second one. The second one, I'll pick Q2C. Okay, doesn't matter which one I use. It's just a variant of the thing. But this one, I don't know whether I can zoom in a little bit, because if I zoom in too much, I cannot see the entire thing anymore. Okay, this is the Easter egg hunt, type of question, but this one is actually easier than your homework, homework assignment, even just by itself. Okay, because some of this stuff is already solved for you. Okay, let me just go ahead and circle the parts that are already solved. The first one here is already a given. I know that I am going to copy the 4 bytes at label L1 into EAX. In other words, okay, is that the only instruction that will change EAX? It is. Okay, there are no additional instructions that will change EAX. In your version of the test, you may not see exactly the same layout, but it is the same nature. So you can solve the problem using exactly the same technique. So in this case, I already know what is in EAX. Now that alone is going to help me with several things, because if you look at the last instruction here, this instruction is going to copy a byte from wherever EAX is pointing to, and it will copy it to BH. So that means, it's not a mystery. This part is already done. It's a done deal already. So let's go ahead and see what is going to be copied to BH, just to see whether it is consistent with this value here. What is going to be in EAX at this point, after this instruction here? If I have to write a line of comment right next to it, what do you think will be the value of EAX at this point? Okay, so EAX has a value of L1 minus 4 after this instruction. Does that make sense? If you look at how I initialize the memory, at label L1, I have a .int construct, which means I reserve 4 bytes, and those 4 bytes will be initialized to whatever expression follows the .int. In this case, it is L1 minus 4, and as a result, I know that after the first instruction, EAX is going to end up with a value of L1 minus 4, not the value at L1 minus 4, but the label L1 and then minus 4. Okay. So what exactly is that byte at L1 minus 4? Well, we can always try to figure it out, going backwards. Okay, this is a dot word construct. If I want to spell out the exact byte sequence on this line, what is that going to be? What is the first byte of this entire sequence?
6E.
Okay, 6E is the first one because it's the least significant byte of the first dot word, and then we have 05, and then we have 7F and 006. Okay. Now, which one is our L1 minus 4? The 6E. Okay, this is L1 minus 4, L1 minus 3, L1 minus 2, L1 minus 1, and L1 is over here. Okay, so everything is consistent because we are expecting 6E in BH. What is BH in EBX? It's bit 8 to bit 15. It's not the least significant part. It is the second least significant portion of EBX. Is that consistent with what we are talking about here? It is consistent. Okay, so that part is not a mystery. It is already done. The mystery part is this instruction here. Let me just highlight the next one. This instruction here is somewhat of a mystery, but it's not too bad of a mystery. Now this is the instruction that you actually have to start with and say, okay, now what do we have to do in order to initialize? What do we have to specify with this question mark here? That's the big question. Okay. But before you answer the question, the first thing you have to do is to say, where in memory am I going to copy to EBX so the EBX will end up having this particular content inside EBX? Okay, let's go ahead and take a look at this byte sequence here, and then we can figure out where in memory can we find something along that line. I'm going to use green here. I'm taking this hexadecimal number here. And too bad it doesn't really have an arrow tool, so I have to draw the arrow by hand. And I don't have a light pen. So Alex, we have to get the light pen going. Okay, so we want to take a look at this here. If I'm going to express these 32 bits or these 4 bytes, in sequence, okay, following the order of the bytes, what are we looking at here? The first byte is the least significant byte, which is going to be 7F, and then the next byte is 6E. But we already know that 6E is overwritten by somebody else. In other words, when we search for that pattern in memory, it can be anything because it is going to be overwritten anyway later on. What about the other 2 bytes, the most significant 2 bytes? And then we have a 5-6, and then a 0-0. Okay. In other words, we are looking for this particular 4-byte sequence in the initialized memory portion, and that's the Easter egg hunt portion of this entire question. Is how do we locate? Can we locate these 4 bytes? Well, actually, there are only 3 bytes in the initialized portion of the memory. So let's scroll up. Well, we don't have to scroll up because it's all down here. There are only several places where you can find 5-6 as hexadecimal. It potentially one of these numbers can also be a 5-6. Does it look like it negative 25 will be in hexadecimal 5-6? Why don't you think so? Because it's a negative number. Okay. If it's a negative number, it means in order to represent it, the most significant bit has to be set for a byte, which means if you express it as a hexadecimal number, it's going to be it has to be greater than or equal to 0x80. Is that making any sense?
Yep.
Kind of. Okay. The same thing applies to 230 because this is 230 in base 10, which is already greater than or equal to 128, which means this is also going to be not 5-6. So 5-6 would be one of these things here. So let's go ahead and see which one is our candidate. Okay, we have this 5-6 here. Do you think this 5-6 is what we are looking for?
No.
Because
The 60 is actually the byte.
it's not at a byte boundary. Okay, it is not at a byte boundary, and there's only one other 5-6 to do. Oops.
Cross it out.
I can undo better. This is the 5-6 that we want. Okay. All right. So what do we have to do to get these 4 bytes into EBX? What is the effective address of this guy here?
L1 plus 2.
Okay. So let's go ahead and do some calculations here. Okay. This one is L1 plus 4. Okay. The address of this thing is L1 plus 4. It's L1 plus 4 because L1 is the dot int that has the content of L1 minus 4. So when we get to the second dot int, it is already at the address of L1 plus 4. Okay. So now we can go back to this instruction here. And let me use the pencil again. Draw an arrow. So we know that at this point, okay, we already know the effective address of the first operand is L1 plus 4. Now how can we make that happen? How can we make the first operand or the source operand to have an effective address of L1 plus 4? Well, whatever EBX is, okay, we have to kind of cancel out the effect of EBX And we already know EAX has a value of L1 minus 4. So somehow we just have to figure out something to stick into EBX. I don't care what to stick into EBX because we have full control over the displacement itself. Okay, we have a lot of degrees of freedom in this case. So then you have to go back and to the previous instruction here, because this instruction also gives you. Okay, let me highlight the instruction that I'm talking about. This instruction here basically gives you all kinds of freedom to load whatever you want into BL. And the first instruction here gives you all the freedom that you need in order to load the most significant 24 bits of EBX. Okay, so you basically have full control over the value of EBX by the time you get to this instruction here. Am I doing? Yes?
So L1 plus 4, I'm trying to figure out why that is. So we have 4 from the dot in of L1 minus 4, right? And then we have, after that, doesn't the 7F come? And then the E6? And then the 5/6?
Okay, let's see. Let's take a look at this one here. Okay, this is L1, right? Oops. It is at address L1. So the next line is L1 plus 4 because dot int takes up 4 bytes.
Yeah, but isn't the next byte 7F? Oh, right.
Yes,
we're trying to get the 7F in there also.
Yes,
Yeah.
exactly. We have to start with the 7F because we want 5/6 exactly to be the second most significant byte. We want 7F to be the least significant byte according to the pattern that we want to load. So that's basically, it matches this exactly, except for the E6 is going to be overwritten by something else, and that's why it looks different. Okay, so now we have all kinds of degrees of freedom. It all depends on how you want to set up everything. As far as I'm concerned, I like it to be easy. Okay, so if you want it to be easy, the first thing you want to do is you can load 0 into EBX. Okay, in other words, you initialize all 32 bits of EBX to be 0 because it's easy to offset the effect of 0. So that's why in here I will change this question mark here to a 0. Okay? Now, what is that going to do? Okay, once I fix the value of EBX, I go back to this instruction here, and there's one more instruction that I have to deal with. Move byte, someplace relative to EAX, to BL. If I want to maintain 0 into EBX, what do you think this question marks, can be to accomplish that? I have to find a byte that is a 0 in the initialized portion of memory. Is there one? We just saw one, didn't we? This guy here. Or there's a hidden 0 right here. Okay, so what is the address of that 0? Okay. So let's annotate that. Okay. The 0 byte of this, particular dot int has an address of L1 plus 7. It's L1 plus 7 because it's the most significant byte of this dot int. The least significant byte is L1 plus 4, L1 plus 5, L1 plus 6, and then the 0 is L1 plus 7. Okay, so we have all the pieces in place now. If I want, this operand to refer to L1 plus 7, I know EAX is L1 minus 4. How do I account for that difference? How many bytes of differences are we talking about here?
11.
There are 11 bytes, okay? So that's why, I have to change this arrow here. So that means this question mark here, I can make it 11 to account for the difference. Because once again, EAX already has a value of L1 minus 4. We want the effective address of L1 plus 7. The difference is 11 bytes. So when I put a 11 here, that will account for those 11 bytes. So I end up having 0 in EBX. Are we doing okay so far with this? Okay. Now, since EBX is 0, which I intentionally made it 0 so that it makes all the calculations easy, and in the next instruction, we wanted the effective address to be L1 plus 4. EAX is L1 minus 4. EBX is 0. So what do you think the question mark has to be in order to give me, the 4-byte sequence that I need? 8 is the answer. Okay. So this is one of the many possible answers, because every single byte that you see here can be used, in the first question mark. I mean the second question mark, and you also have full control over the most significant 24 bits of EBX. In other words, for this particular question, there's a very large number of possible answers. I have to kind of evaluate every single one to see whether your answer is going to do the trick or not. Are there any questions? Yep, go ahead.
Where's the quarterback in this whole play here?
He got sacked from the get-go. I mean, is that okay? I mean, do you guys understand the approach of this problem? Okay. Let's go ahead and save this one. And we'll take a look at the third question. The third question, I'll look at the first version. Okay, here's the third question. The third question, has 2 parts. The first part is to specify a single value to replace the question mark here, so that the sine, overflow, and the carry flags are all set when the program stops at the checkpoint. Okay. So, and this is also a compare instruction, which later on in the class I said, change that to a subtraction instruction instead of a compare instruction. Okay. What is the equation? How do we define the overflow flag for subtractions? Let's take a look. I mean, we should know that, because that's going to be the key. I mean, this is the first thing you have to figure out is what is the definition of the O flag, which is also given in the instruction. In my cheat sheet on page 1, there's also the definition of the overflow flag in a subtraction. Is that right? I hate to make an assumption that is wrong, so let's go ahead and take a look at that. Bigger. Okay, the overflow flag is one if and only if the sign of the result of add or subtract does not make sense. So I did not give you the full definition in terms of bitwise operations, but this is we did talk about it in the class. So let's go ahead and take a look at this part here. Okay. We already know we are subtracting a negative value from EAX. If I subtract a negative value from a negative value, what can the sign of the result be?
Anything.
It can be either, right? It can be positive, can be negative. In other words, if you subtract a negative quantity from a negative quantity, there's no way the overflow flag can happen. Okay, so we have to toss that out the window. The only case when the overflow flag will be set in a subtraction is you're subtracting a negative value from a positive value. And if you end up with a negative value, then the sign of the result does not make any sense. Okay, so what we are looking for here is to take a look at the overflow flag, and then we say, I don't know how to put it, except we can put it this way. We can say bit 7 of x, which is the number that is being subtracted. That has to be a positive number, which basically means I have to take the negation of that. And y, which is in this case negative 34, needs to have the most significant bit set. The result, or in this case the difference, also needs to have the most significant bit set. This is what we are using in order to determine whether the overflow flag is going to be turned on or not. But hold on a second here, Tech, when you define the overflow flag for subtraction, there are two parts to it. This is only one part of the whole thing. How come I can just kind of ignore the other part? I can ignore, yeah, go ahead.
Well, we need the county flag.
No, we need a sign flag.
Sign flag.
Yeah, because we need the sign flag to be set as well. The other equation will have not D7, which means the sign flag of the result is cleared, which would not meet our requirements. This is the only one that will meet our requirements, is to have a positive number minus a negative number and somehow end up with a negative number. Are we doing okay so far? Just looking at the definition of the overflow flag itself. Now that gives you some restrictions already, because out of this you already know that x needs to be non-negative. Now non-negative means the most significant bit has to be off. Now I made one mistake here because I changed the nature of the question. The problem is I have EAX, and the instructions are byte-wise operations. So I would basically take that into consideration. If you give me examples that will work for 32-bit operations, you get full credit. If you give me values that will work with 8-bit operations, I will also give you full credit. Okay, because the instructions are ambiguous. One part of it suggests it's 8-bit, the other part suggests it is 32-bit. So you can use either one, and I will give you full credit for either case. Okay. Now, how can I make this happen? What does it mean when D7 is set? The most significant bit of the difference is set. That means, okay, what if I look at it from the perspective of just bits, not there's no sign associated with it. It will start with a 1. The most significant bit is going to be a 1. Okay. So what is the least value that has a 1 as the most significant bit? 1 followed by 7 zeros. 6, 7, 7, 7. 1. Okay, 1 followed by 7 zeros is the least bit pattern that has the most significant bit being a 1. And we are subtracting 34 in order to get that pattern to happen. Okay. Now, what is 1 followed by 7 zeros? If I convert it into an unsigned integer, what is that? 128. So what this question is really asking is, I need to find x so that x minus negative 34 in this case is exactly 128. If I can find an x that will satisfy these requirements, I'm good. It is one example already. So the question is, can I find a pattern like this? Well, this is algebra, so you can basically move, you can add negative 34 to both sides. So one side becomes x, and the other side becomes 128 minus 34, which is, what, I cannot do arithmetic. 94? Is that right?
Yeah.
That looks right to you? Okay. So this question mark being 94 will give you one example. Okay? But then the second part of the question is, identify or specify one end of the range of the values that will make this happen. And then you have to go to the opposite end as well to basically look at the range of values that can make this happen. Now, how do we do that? Well, x can start with 94. Okay, I know that x cannot be less than 94, because if x is less than 94, then if x is less than 94, then it won't get to 128. Is that making any sense? You can just try 93, because 93 minus negative 34 is only 127, which will not trip the overflow flag to happen. Is that making any sense? So in this case, not only am I solving for only one case, I'm also specifying that 94 is not just a value that works. It is also the smallest value that works. So my only job remaining is to figure out what is the largest value that will also work. Okay? 255 is a good guess because 255 is 1, 1, 1, 1, 1, 1, 1, 1. But remember, I need the most significant bit of that number to be 0. And the largest unsigned number, signed or unsigned, that has the most significant bit of is 127. So 127 is the end of the range. And it doesn't matter which way you specify. You can specify 127 and then 94 because I did not specify which one is. I did not specify the smallest and then the largest, so you can reverse those two. Okay. Are there any questions about this one? Yep.
How do you get 128? Turn 1000 to.
Because 128 is the smallest unsigned number that has the most significant bit being a 1. Attack, I don't know powers of 2. Well, the first page on the cheat sheet gives you a list of all the powers of 2 that you need in order to answer these questions. Yep.
It says the carry flag has to be set.
The carry flag will be set in this case. Now, how do we know the carry flag is going to be set when you subtract the negative 34 from 94?
Because 0 minus 1 gives you a borrow of 1 no matter what.
Because negative 34, what is the unsigned representation of the bit pattern that also represents negative 34?
1 something 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 something.
It's going to be bigger than 128.
Yeah, well, it has a 1 in it.
Yeah, exactly. It's more than 128, which is more than enough because 94 is less than 128 plus. Okay, and that's why if you subtract 128 from 94, there will be a borrow. Okay. Any other questions about this one? No. Okay. Let me save it first. The original question, assuming that people can actually have access to GDB, was move L and compare long, because that just, but that's not any more difficult. What if I make it so that it is compare long and move long instead? How would you change the answer?
The numbers would just be larger.
You just have to fill it up with a bunch of ones in binary. Yep. Okay. So let's go ahead and take a look at the last question. The last question is question number 4. We'll take a look at the B version of that. And I have decided to designate 1 out of the 4 questions as an extra credit question. That means if you get only 3 answers right, but all 3 answers are answered perfectly, you get 100% already. If someone in the class, I don't know who yet, gets 4 out of 3 right, that person has 133% of all the possible points for this particular test. I don't know who's going to get it. I think someone may get more than 100% in this test. I don't know who's going to get it. Yep.
So if we
You
get
gotta get
80% on all 4 of them, do we still get the 100% just like normal?
If you get,
The 80% on all 4 of them?
well, let's take a look. If you get 80%
I'm
on
just
each
making sure
one,
that's how it's going to work out if that
so
happens.
you have, okay, so you have 80% from the first one, 80% from the second one, and so on, right?
Yeah.
Then you already get more than 100%.
Okay. That's all I'm worried about.
Okay? Now you said that, I did not. Okay, this is the last question. The last question is, okay, I want to multiply a number by 98. And since we have not talked about the multiplication instruction, we definitely cannot use the multiplication instruction. So there are some restrictions here as to what instructions you can use in order to accomplish this. And I have it narrowed down to 1 move L instruction and up to 9 add L instructions. Okay, if you do it smart, you don't even need 9 add L instructions, but you have up to 9 add L instructions to use. There is no operand restrictions. Okay, you can use any operand that you want to use. And here, just to be very clear, when I test your code, I will reinitialize EAX to a different value. So that means you cannot just figure out what is 23 times 98. You have to make your code for any number times 98. Okay, that's the key. Okay, so for this one, I think I will answer the question like this. Okay, and change the color. Okay, so we have a number, okay, whatever is in which register, EAX. So I'll just call it X, okay, instead of typing EAX, I'll call it X. We have to figure out what is X times 98 in this case. So I will go ahead and read the notes, the hint here. A big hint, the following instruction doubles the value of AL. I intentionally did not use EAX because it is the concept that matters. It is not the exact register that is the important part. So I don't want people to just have to say, oh, I just copied this instruction, because if anyone copied the instruction, the width would have been wrong. Okay, it is just adding a register to itself will double the value of the register. And then there's another hint, look at the values using the binary representation. Okay, so if you look at the binary representation of 98, okay, and some people used the binary representation on the wrong value, which is, I guess, 23 in this case. That would not be very helpful. Okay, you have to look at the binary representation of the multiplier that does not change, because since I will change the value of EAX anyway, there's no way to anticipate the binary representation of that number, when I actually test the code.
Will you give partial credit to people who use the wrong number?
I'll take a look at what it looks like, because it's not possible with 23. It's not possible because 23 is 16 plus 4 plus 2 plus 1. So you won't have enough instructions to get it done. You might be able to get it done by using just that number. Okay, but here I want to take a look at 98. 98, if you look at the binary representation, it has a 64. It has a 32, and it also has a 2. Okay? Now, you might want to say, but why do we want to look at it this way? Well, I would do something that's even worse, because I can say, the first one is x times 64, x times 32, and x times 2. Okay? Now, why do I want to express, this term, from a very simple term here to something that looks kind of ugly? Because we know how to find powers of 2 of x. Okay, because I know if I keep adding EAX to itself, I can get EAX, I can get twice EAX, I can get 4 times, I can get 8 times, and so on. So now the question is, what am I going to do to it? I know that I need a bunch of instructions like this. So giving me 6 of these instructions is not going to worth a lot of points, because we already know that this is the trick. There will be some points, just not a whole lot. Okay. Now I can stop here. I can stop here because 64 is 2 to the power of 6. Okay. In other words, if I go back here and write a comment, I can say this is 2x, this is 4x, this is 8x, oops, this is 16x, this is 32x, and the last one is 64x. The question now is, what am I going to do with these multiples of x? 2 to the power of something of the value x.
You take the powers of these and add them into ECX or whatever value you gave us.
Exactly.
At the required intervals.
Now there is it depends on, if you do it smartly, you can just use 2 more add instructions and 1 move long instruction. If you want to do it the easier way, to initialize everything first and then add later, then you can use the last add instruction that you are allowed to use. So I'm just preparing for people who want to do it that way, because optimization is not really a part of it's not a key to this one. So one way to do this is basically tap it at the right points. Okay? In this case, in this particular case, I have 98, So I need one tap when I have 2x here. So I will just go ahead and tap this one here. I need another one when I have 32x, which is in here. And I need one last one when I have a 64x. Okay? So I'm going to insert additional instruction here. So at this point here, between the 2x and the 4x, I would use an add out instruction to add EAX to the final result. Oh wait, I'm trying to do it the easier way. So I can move because I can destroy the original content in EBX. So I can move EAX to EBX at this point. So EBX, okay, EBX is 2x at this point. Is that working out so far? Okay. So at the second tap point, I would do about the same thing, but I'm not going to move anymore because one, I can only use one move instruction, and two, if I move again, I would have destroyed the 2x that is already stored in EBX. So this time, I have to use the add out instruction to add EAX to EBX. So at this time, EBX will be 34x, and the next one is going to be add out EAX again to EBX. And at this point, EBX will be exactly 98x. So that's basically the approach. This question really, asks a few things. One is, do you understand the add out instruction? Particularly, you can double the value of something really quickly. That's part of the hint already. The second question is, can you sequence the instructions so that you can accomplish the multiplication, but it really is testing whether you can see things from the binary perspective. Okay, how many multiples of powers of 2 do we have when you multiply that particular number? Okay. Are there any questions about this one? Yep.
It's not a question, but just a comment. You just graded my whole test. The 4 randomly selected were my test.
Really?
Yeah.
Well, let's see. We have 3 versions for the first, 3 versions for the second, 3 versions for the third, and 3 versions for the last. So we have 3 to the power of 4, which is 81 possible combinations.
You got mine.
And I get yours. And there are not enough students in this class to actually use up all 81 possibilities.
I thought that was pretty cool.
That is just interesting, yes. Are you sure you don't remember it wrong?
No, I recognized every question.
All right, well, that's cool.
I remember the values.
It's also possible that my so-called random generator is not really random.
Does your get random function return 4 is chosen by a fair dice roll?
Okay, well that's those are all the answers. So once again, if you want to open up these files, you have to use Zerno to open it. And I'll just point you to a place where you can download Zerno. Pretty much if you type in Zernal, Xournal, you can find the website already. You can also find Zernal in a portable format because many of you already have your virtual machine on a USB thumb drive. So downloading and installing Zernal as a portable application. Oh, I guess they don't have a portable version. No. But I think it has a Windows port. Let's check it. Yep, binary, Win32 binaries. So you don't even need to run Linux to use Zernal. You can use Windows
It's
instead.
experimental.
Yeah, close enough. Yep.
Since we can't use the computers for the test, can we do a project instead of the next test? Because you said either or on your syllabus. So.
Either or.
You either.
It depends on the nature of a class. For a programming class, it's not going to be a
that's
project.
a generic syllabus.
Yeah.
I see. Oh.
Yeah. If it's let's say a Linux security class, then it might be a project. I give people a, insecure, virtual machine, and they have to lock it down. But for a programming class, it's pretty hard to do it that way, unfortunately. However, next time, because I know the scheduling of the lab already, next time we can schedule to take the test online, but it will use the lab time instead of the lecture time of this class. Okay, the lab will still be kind of occupied at this time, but the lab time that we normally use, which is 8:30 to 9:45, during that time, the lab, should be free enough that we can all fit into the lab. Yep.
So how about we take that lecture time before the test and go over the test like we just did now?
No, I don't think it still wouldn't help.
I give you all the possible answers, but I don't tell you the answers to which question.
Oh, that's the easy part.
Since we're in the lab, we can just plug them in and try.
Plug in and try.
It's so hard to test your theories on paper.
Yeah.
But that's why I'm only grading on the the concept, whether you get the right approach, to solve the problem. Now, doing it in the lab is not always good, because I have seen a lot of cases when I have actual practical tests in the lab. Some people get very obsessive to get everything right, okay? Because there's a way to get it right now. You have all the tools, and there's a way to tell that your program is actually not working. So some people spend too much time on a single question because they could not get it right, even though most of the concepts are down already. It's just missing that one last instruction, and it would not work. And some people just waste all the time on one single question and did not have enough time to actually get enough points to pass the class. So so that's the flip side. That's a flip side to going to the lab and actually have the tools with you. With a paper test, the way we have it now, there's no way you can be obsessive like that, because you can only look at your own code and think, okay, I think that's going to work, or it's close enough, and then you have to move on. So there's a plus and minus to to each approach. But if the class has a consensus and want to do it in the lab, next time we can do it in the lab. It's just that we can only do it in the lab time of this class. Yep.
So what are we gonna do with the lecture time?
We'll just talk about new stuff.
Or you can do the review of the practice exam during that lecture time.
We could do that too, but I have been told that the practice exam was not really related to the actual
It's
exam
better
in
than
this
nothing.
case.
I'd rather have some sort of review of what we tested.
Okay, well we could do that. Okay, so I'm going to pass the test back to you guys, even though it has not been graded fully yet. That's because I ran the entire pile. You can see the thickness of this pile here through my scanner. So everything, I only scanned it at 300 dpi. So if you write very, very small, it is possible that I might have missed a few pixels here and there. But I kind of scanned through the whole thing myself too. I don't think anyone is writing so small that at 300 dpi I cannot capture everything. Okay, so I'm going to pass this back to you guys. This is all alphabetically ordered now. You can kind of imagine how much time I have to spend to do all this. First of all, I have to sort everything in the right order. Then I have to take the staple out. Then I'm going to scan it, run it through the scanner. The scanner gave me a 1.2 gigabyte file after I scanned every single one. In grayscale mode. In grayscale, just grayscale, not color. In grayscale mode, but once I used threshold to turn it into just black and white, it became like 12 megabytes instead. Yeah.
Don't
You
have
didn't
a
save
TA
it in
for that,
2-bit?
Hmm?
You didn't save
Yes,
it in
I
2-bit?
did. The last, I processed it, and that's the last version. Okay, so
You need a grad student or something.
yeah, it doesn't happen around here. Okay, Adami. A-D-A-M-I.
She's not here.
She's not here?
Yeah.
Okay, is that her last name?
Yeah.
Okay, just want to make sure. Okay. Is it Ilo? Okay. It's all alphabetically ordered, so you can already expect the random names. There are no points, no scores whatsoever on the test, so so there's no way you can be disclosing your score to anybody else, unless it is blank, of course.
Or mine. I can tell you exactly.
Okay, so I'm from. Okay. So I have to make sure I use the right number of pages, so you don't get the first page of the following question.
You didn't re-staple it for us?
No.
Oh, don't worry. Staple it.
I thought about doing that, but then it was already 1:30 a.m. and
You don't have a copy of the staple?
Okay, Armstrong, Austin. Eric. That's it.
Would it help if someone counted out the pages and just handed you the specs?
Well, it gets easier because it's a thick pile right now. Okay, does that here? Baran? She's not here? Okay. Save that. Alex. If I seem to recognize some people's name and not other people, you not feel offended. Because, just because I remember somebody's name, some student's name is not always, reflecting something that's good or bad. It's just, I know certain people. Botgen? Okay. You're not Botgen. Botgen.
Oh,
B-O-T-D-G-E-N.
Oh, yeah. I'm not.
Yeah.
Sounds pretty cool.
Okay. Bowers? B-O-W-E-R-S? Michael? Not here. This is kind of like a very slow way to take roll 2.
Well, you should do this every
I like
class
you brought a
then.
roll sheet today.
That's why I don't need a roll sheet today. Vincent?
Speaking of roll, can we pause the video for this?
That's a good question,
right.
actually.
We should have a little USB webcam. Turn it around so that you guys can see me walk around and
Yeah.
passing the test.
All I'm saying is I don't want to be watching a half hour of you calling out our names.
Using the wrong pronunciation.
Yeah.